Hey everybody, Mr. Scala coming at you digitally, trying to do either a review or for those people who are out right now, keeping you up to date on what we've been working on and doing in class. We did one of our vocabulary words is energy transfer, and that's just the movement of energy from one place to another. And sometimes matter gets hot or gets cold as a result of energy transfer. Change in temperature is evidence that energy transfer has taken place. When we talk about energy, we talk about one of our vocab, the conservation of energy, which means energy is not created or destroyed, it only changes form. And conduction is energy transfer that results from direct contact. So, we have some energy transfer big ideas. Number one, the particles that make up matter are in constant motion. So, all particles are in constant motion, solid, liquids, and gases. As a result, the particles have kinetic energy, remembering that kinetic energy is just the energy of motion. The level of kinetic energy of the particles in a sample of matter determines how hot it is. So the greater the kinetic energy of the particles in a sample of matter, the hotter it is. So more kinetic energy means it's hotter. Important idea number two. Energy transfers as a result of particle collisions. When a fast-moving particle collides with a slow-moving particle, the one that was going fast slows down, and the one that was going slow speeds up. And an analogy I like to think of, because it's really good this time of year with all the snow we've gotten, is a car at a stop sign and a car that can't stop because of the ice. So the car at a stop sign, let's say that car that can't stop hits the car that's at the stop sign. The car at the stop sign is going to move forward as a result of that car that's moving faster than it hitting it. And the car that hit the one at the stop sign is going to slow down because it's giving its energy to the car at the stop sign. So energy transfers when particles collide. And we have a good animation that shows particle collision. So in gas, particles fly through the space. Some fly fast, and others have less kinetic energy, move more slowly. Frequently, particles collide, and when they do, they transfer energy from a fast-moving particle to the slow-moving particle. So it always goes from fast to slow, just like energy always transfers from high kinetic energy to low kinetic energy. So we're going to watch it again. We're going to look at it with our lower speed. You see our slow particle coming in, and it hits our faster moving particle. We'll watch medium speed, and then, of course, high speed. If we're looking at these, we'll see our blue is our slow moving one, and our red is our fast. When they collide, they're going to turn purple to show that they actually end up going the same speed after they collide. And that's what particles do. They average out. The fast one gives the slow one kinetic energy, and then after they're moving at the same speed. So when we heat up a substance, you are increasing its kinetic energy. In the case of the water mixing, you did that by transferring the kinetic energy through conduction, by directly mixing our hot and our cold water together. So, and here is a good animation of this. So this animation shows when a hot and cold water are mixed. The water particles in the two cups are not mixed in the beginning. They just represent two different colors. And the colors used so you can observe what happens to the particles that start in the hot water and what happens to the particles that start in the cold water. Pay attention to kinetic energy, so how fast the particles are moving. So we have our fast ones over here in red and our slow ones over here in blue. When we mix them together, they're going to collide and they're going to average out. So it's an average between our hot and cold. One of the things that we talked about in class is that it can't be hotter than our original hot one, and it can't be colder than our original cold. It has to be somewhere in the middle. I'm going to watch it again. The particles are hitting each other, bouncing off. The fast ones are giving energy to the slow ones, so the fast ones are slowing down. The slow ones are speeding up. So our online thermometer. We made a thermometer in class. It was when we had our vials with the blue water, the stopper, and our plastic tube on top. So in that, the thermometers are used to measure temperature. So how can we remove energy from the thermometer? In class, when we put it in our hot water, it went up the tube. And when we put it in the cold water, it went down the tube. So in the hot water, it expanded. It took up more space. So that's what filled up the tube. And in the cold water, it contracted and went down the tube. So how can we remove energy from our thermometer? Well, one way we can do it is by moving it into a colder substance. So if I have a thermometer in our classroom here, let's say it's 70 degrees in here, and I take it outside where it is a lot less than 70, it is transferring its energy into the environment around it. So it's warming up those particles that collide with it, slowly cooling the particles inside the thermometer till they're the same speed as the particles that are outside. And this is a very good example. So, looking at the thermometer filled with red alcohol in a pot of water, look at the close up, and it's not to scale view of it though. We have our alcohol particles in red, our glass particles that are in gray, and our water particles that are in blue. So, first thing we're going to do, we're going to heat up our water. So, we turn on the burner. So, the energy from the water, from the heater, transfers to the water molecules. The water molecules start to move faster. You can see they're moving a lot faster. Then the next thing that happens is the faster moving molecules hit the glass thermometer bulb. Energy from the water transfers to the molecules in the glass of the thermometer bulb. The glass molecules start to move faster. And what do we think is going to happen next? Well, if you predicted the glass molecules are going to transfer energy to the alcohol particles, you were correct. We watch the thermometer goes up. So the vibrating gas molecules hit the alcohol molecules inside the thermometer bulb. Energy transfers to the alcohol molecules. The alcohol molecules move faster, and the alcohol expands and moves up the thermometer stem. When we're talking about expanding, you can notice the size of them doesn't change. When we talk about expansion, it means that they're getting further apart. Now we're going to look at what happens when we cool our water. When we turn the heater off, the energy radiates from the water to the environment. So the water molecules have less energy and move more slowly. So when it says radiates to it, transferring to the environment, all of the air particles that are all around this water are running into the water, running into the pan, slowly taking that energy. So it's giving the water and the pan are giving its energy to the environment around it, so the air particles. And what's going to happen next is the glass molecules transfer energy to the cooler water. So the gas molecules then have less energy and move more slowly. Remembering that energy always goes from high to low or hot to cold. So our hotter particles are transferring their energy to the slower, colder ones. And what do we think is going to happen last but not least? Well, if you said the alcohol particles are going to give their energy to the glass particles, you were correct. And in class, we kind of talked about it's a chain reaction. So because our water particles got hot and because the thermometer's in the water, well, it transfers to the glass and then it transfers to the alcohol particles. So it's a chain reaction. So if one got hotter, they all got hotter, the kinetic energy increased. If one got colder, they all got colder, kinetic energy decreased. All right. And then we looked at our big takeaways. We wrote these in our binder. Not all of it, just what's in bold, because those are big takeaways. Kinetic energy is directly related to particle speed, temperature, and volume of matter. If one goes up, they all go up. So for example, the more kinetic energy you have, the faster the particles move, the higher the temperature it is, and the more space, the volume it takes up. The faster the particles go means more kinetic energy, higher temperature, and more volume. So if any one of these kinetic energy, particle speed, temperature, and volume go up, they all go up. If any one of those, they are directly related. If one goes up, they all do. Number 2, kinetic energy is directly related to particle speed, temperature, and volume of matter. If one goes down, they all go down. Number 1 and 2 are very similar, but it's just the opposite ends. Number 1 is focusing on if one goes up, they all do. And number 2 is looking at if one goes down, they all go down. And number 3, particles do not change size. They can get further apart or closer together. So the particles themselves do not change size. And when we're talking about them getting further apart, that's our expansion. And if we're talking about them getting closer together because they are getting colder, that's contraction. And closer together because of force is our compression. And gas is the only one that can be compressed. We can't compress a solid and we can't compress a liquid because their particles are already touching, or liquid particles are already touching and solid particles are connected. So energy transfer is due to particles colliding. So when they hit is where that energy transfer takes place. And energy transfers from high to low always. Always, always, always. High energy transfers into low energy. AKA, hot things transfer their energy into colder things. Then in class, we looked through some scenarios. Each group worked with their lab group to look at one of the given scenarios. And in the scenarios, they drew out a model and they labeled the particles and they showed what happened in their example. One of the big things we really focused on is that you should always talk about, should be stating the energy transferred from this object to this object because. So it transferred from, number one, it could be transferred from the hot mug, the hot coffee in the mug, to the cooler air particles, because energy always transfers from high to low, hot to cold. The big two we really focused on, because two of these are going to be focused in an assessment coming up tomorrow, we really focused on putting a warm water bottle in a cold cooler with ice, and putting a warm baby bottle in a hot pot of water. Those are some ones that we focused on. Nudge, nudge, wink, wink, because I want you to do as well as you can. All right. That's what we did today in class. Have a wonderful rest of your day, and I hope to see you soon. Bye.